Tonight, we need to fix something that most people carry around without realizing it's wrong. When we picture the solar system, we reach for a particular image almost automatically. A golden sun sitting at the center, surrounded by a neat family of planets sweeping along clean circular paths. Everything spaced out in a tidy progression, color-coded for clarity, labeled for easy identification. Maybe there's a thin ring sketched in around Saturn, maybe a handful of asteroids floating peacefully in a loose band between Mars and Jupiter. The whole thing has a kind of quiet order to it, the feeling of a system that knows what it's doing, that has been doing it reliably for so long that the result is something almost serene. That picture is wrong, not slightly wrong, not wrong in minor technical details that only specialists would care about, wrong in the way that matters, wrong about the nature of the thing itself. The solar system is not orderly, it is not calm, it is not designed for our comfort or survival. What it actually is, what it has always been beneath the reassuring diagrams, is one of the most violent, extreme, and unforgiving environments imaginable. It is a place where a thermonuclear explosion has been running uninterrupted for nearly 5 billion years, where billions of rocky and icy projectiles still orbit on paths that cross our own, where neighboring planets stand as direct evidence of how quickly everything can go catastrophically wrong, where the gravity of a single massive planet has spent 4 billion years flinging debris toward the inner solar system, where the structure of the Milky Way itself reaches in from the outside and periodically stirs the outermost darkness into sending new threats falling inward. We are alive inside this, not safely removed from it, not watching it from a comfortable distance. Inside it, separated from its full hostility by a thin magnetic bubble, a shallow ocean of air, and 93 million miles of vacuum that, by the standards of the solar system, is barely any distance at all. By the end of tonight, you will not be able to look at a solar system diagram the same way. And that, honestly, is the point. Because the accurate picture is not just more honest, it is more interesting, more strange, and more worth understanding than the comfortable version that most of us were handed and never questioned. If you love going deep on how the universe actually works, rather than how we like to imagine it does, take a moment to subscribe. It helps this channel reach more people who want the real version. Now, let's begin. Start with something simple. The diagram is lying to you about distance. Not because the people who drew it were careless. They had no choice. The solar system is so vast that drawing it to true scale is essentially impossible within the space of any printed page or classroom poster. The compromise that gets made every time is to shrink everything down, compress the distances, push the planets closer together so they all fit within the frame. The result is a picture where the solar system looks like something you could walk across in an afternoon. That feeling of manageable scale is exactly what causes the problem. Here is what the distances actually are. Mercury orbits the Sun at roughly 36 million miles out. Venus sits at about 67 million miles. Earth is at 93 million miles, the number we use as our baseline unit of measurement and call one astronomical unit. Mars orbits at around 142 million miles. Now consider that the distance between Earth and Mars at their most separated, when they are on opposite sides of their respective orbits, exceeds 250 million miles. We have sent robotic spacecraft across that gap, and the fastest of them needed the better part of a year to make the crossing. That's just the inner solar system, the supposedly compact neighborhood closest to the Sun. Jupiter sits at roughly 484 million miles from the Sun. Saturn orbits at close to 890 million miles out. Uranus is at nearly 1.8 billion miles. And Neptune, the most distant of the 8 recognized planets, orbits at just under 2.8 billion miles from the Sun. If you set out to drive from the Sun to Neptune at a steady highway speed, never stopping, never sleeping, you would not arrive for over 4,500 years. And Neptune is not where the solar system ends. Beyond Neptune, the Kuiper Belt stretches outward from about 2.8 billion miles to roughly 4.6 billion miles from the Sun, a broad disk containing hundreds of thousands of icy bodies, some of them large enough to qualify as dwarf planets. Beyond even that lies the Oort cloud, a vast spherical shell of icy material that begins at perhaps 2,000 times the Earth-Sun distance and extends outward to somewhere between 50,000 and 100,000 times that distance. The outer boundary of the Oort cloud sits roughly 9.3 trillion miles from the Sun. That structure, that unimaginable shell of dark frozen objects in the near absolute cold of deep space, is still considered part of our solar system, our neighborhood, our home. Absorbing that scale properly does something to the comfortable diagram. The neat little family portrait dissolves. What replaces it is something more accurate and considerably more sobering. A star surrounded by mostly virtually nothing, with matter scattered across distances so vast that traveling between individual planets would consume human lifetimes, let alone reaching the true outer edges of the system. The vast majority of the solar system by volume is empty. What fills that emptiness, or more precisely what moves through it, is the actual story. The scale diagrams compress not only distances, but danger. When the asteroid belt appears as a narrow ring slightly wider than Mars's orbit and Jupiter's, it suggests a manageable, well-contained zone of debris. The reality is a region spanning nearly 100 million miles in width, containing millions of objects, governed by gravitational mechanics that continuously redirect some portion of its contents toward the inner solar system. The diagram doesn't show you that. It can't. The compression hides it. The Oort cloud doesn't appear on most diagrams at all, because if the sun were drawn as a circle 1 inch across, the outer edge of the Oort cloud would need to be represented more than 3 miles away from it. No classroom poster accommodates 3 miles. So, it gets left off, and with it goes any visual sense that our solar system extends into a region where the galaxy's own gravitational structure can reach in and disturb things. Everything that follows in this video is a consequence of understanding the solar system at its true scale, not the scale of the diagram, the real scale, the one that contains the distances, the emptiness, the objects, and the forces that make this environment what it actually is. Everything begins with the sun, because the sun is the solar system's dominant object, its overwhelming source of energy, and its primary source of ongoing hostility. To understand the solar system correctly, you have to understand what the sun actually is, not the gentle warm lamp of popular imagination, but the specific, extreme, and continuously violent object sitting at the center of this system. The sun is a thermonuclear reactor. At its core, temperatures reach approximately 27 million degrees Fahrenheit, around 15 million degrees Celsius. The pressure at the core is roughly 340 billion times greater than the atmospheric pressure at Earth's surface. Under those conditions, the process that powers the sun becomes possible. Hydrogen nuclei, individual protons, are forced close enough together that the strong nuclear force overcomes their mutual electromagnetic repulsion, and they fuse, forming helium nuclei and releasing energy in the process. The sun converts somewhere in the neighborhood of 600 million tons of hydrogen into helium every single second. Every second, without pause, that transformation has been occurring for approximately 4.6 billion years. The energy released in the core does not simply shoot outward in a straight line. It begins a journey through the sun's interior that takes far longer than you might expect. In the radiation zone surrounding the core, energy moves outward in the form of photons, but those photons are continuously absorbed and re-emitted by the dense solar plasma, scattering in random directions with each interaction. The net outward drift of this energy is extraordinarily slow. A photon generated in the solar core may take anywhere from tens of thousands to over 100,000 years to make its way from the core to the solar surface. When it finally does, it shoots out into space and covers the 93 million miles to Earth in approximately 8 minutes. The journey from core to surface takes 100,000 years. The last leg across open space takes 8 minutes. The surface of the sun, the layer called the photosphere that we see when we look at it through a properly filtered telescope, burns at roughly 10,000 degrees Fahrenheit, around 5,500 degrees Celsius. That sounds extremely hot. By the standards of the solar system's most extreme environments, the photosphere is actually the cool part. Above the photosphere lies the chromosphere, a thin transitional layer, and beyond that the corona, the sun's outer atmosphere, which extends millions of miles into space and reaches temperatures of 1 to 3 million degrees Celsius. The corona is between 100 and 500 times hotter than the surface beneath it. For any other heat source, this would be impossible to understand. If you held a candle under a sheet of paper, the paper gets hotter closer to the flame, not cooler as you approach the flame and then dramatically hotter again once you move away from it. The sun violates that basic intuition, and nobody has fully explained why. The leading explanations involve two mechanisms. One centers on Alfvén waves, a type of magnetohydrodynamic wave that propagates through the corona, carrying energy upward from below and depositing it in the outer atmosphere. The other involves nanoflares, tiny explosive events driven by the reconnection of magnetic field lines in the corona, each one individually modest in its energy release but collectively capable of heating the corona to observed temperatures. Which of these mechanisms dominates Whether both are necessary, whether something else is also contributing, remains an active area of solar physics research. The mystery of coronal heating has been studied for decades and has not been fully solved. What is not in dispute is the consequence. The corona is so hot that the sun's gravity cannot hold it. The gas simply has too much thermal energy to be retained, and it flows outward continuously in all directions. This outflow is the solar wind, and it represents the sun's most immediate and persistent physical influence on the rest of the solar system. The solar wind is not a metaphor. It is a real stream of physical matter, mostly protons and electrons, with smaller contributions from helium nuclei and trace heavier elements, flowing outward from the sun at velocities typically ranging from 250 to 550 miles per second. These particles do not drift gently. They blast through the solar system at speeds that, compared to anything indeed, ordinary human experience, are almost incomprehensible. The solar wind reaches Earth in roughly 3 to 4 days after leaving the sun. It reaches Jupiter in 10 to 20 days. It reaches Neptune in about 6 months, and it continues outward beyond Neptune, beyond the Kuiper Belt, pushing outward until, somewhere around 11 billion miles from the sun, the pressure of the interstellar medium finally overcomes it, and the solar wind is stopped cold at the boundary called the heliopause. Voyager 1 crossed that boundary in 2012 after 35 years of continuous travel. Everything within that 11 billion mile sphere feels the direct physical breath of the sun at all times. The solar wind is also not uniform. Regions of the corona called coronal holes, areas where the sun's magnetic field opens outward into space, rather than looping back to the surface, allow faster, denser streams of solar wind to escape. These high-speed streams eventually catch up to the slower solar wind ahead of them and compress it, forming structures called corrotating interaction regions that rotate with the sun and sweep past Earth repeatedly. They are a regular, predictable feature of the solar wind environment, and when they arrive, they reliably produce moderate disturbances in Earth's magnetic environment. But the solar wind is only the beginning of what the sun does to this solar system. The more dramatic, more potentially consequential expressions of solar activity are occasional, not continuous, and considerably more violent. The sun's surface is not static. It is covered in a constantly shifting, tangled, highly dynamic magnetic field, and when that field becomes sufficiently stressed and tangled, it releases energy. The two primary forms of that release are solar flares and coronal mass ejections, and while the names might sound technical and therefore somehow distant from ordinary life, the consequences of the largest events in these categories are anything but distant. A solar flare is an intense, rapid burst of electromagnetic radiation originating from a magnetically active region of the solar surface. Flares release energy across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. The most energetic flares release quantities of energy equivalent to billions of nuclear weapons, detonated simultaneously, all of that energy delivered within a window of minutes to hours. The radiation from a large flare travels at the speed of light and arrives at Earth in approximately 8 minutes from the moment of eruption, giving essentially no warning time for any system that might need to respond. When that radiation hits Earth's upper atmosphere, it ionizes the gas at high altitudes, disrupting the propagation of radio waves that bounce off the ionosphere for long-distance communication. High-frequency radio communications, the kind used by aviation and emergency services over long distances, can be completely blacked out across the sunlit hemisphere for the duration of the flare and for some period afterward. GPS accuracy degrades because the signals from satellites pass through the ionized atmosphere and are refracted in ways the systems aren't designed to account for. For aviation flying polar routes, where much of the protective atmospheric shielding is thinner and radio communications depend heavily on those bounced signals, a major flare requires rerouting flights to lower latitudes, away from where the disruption is worst and away from the elevated radiation environment at altitude. Flares are categorized by their peak X-ray output, ranging from Class A at the quiet end of the scale through B, C, M, and X, with each letter representing a 10-fold increase in energy output. Within the X class, the largest category, events are assigned a numerical multiplier. The largest flare measured by satellites occurred in 2003. It was so energetic it saturated the measuring instruments before they could record the true peak, and subsequent analysis estimated it at around X45, a level roughly 25 times more powerful than events that are already considered severe in operational hazard planning. That particular event was produced by an active region on the Sun that happened to be rotating away from Earth at the time of the largest eruption. The geometry saved us from the worst of it. Coronal mass ejections are different in nature from flares, though the two often occur together. Where a flare is primarily an electromagnetic event, a burst of radiation, a coronal mass ejection is a physical event, the actual ejection of magnetized plasma from the Sun's corona. A large coronal mass ejection can expel several billion tons of plasma into space. That cloud travels more slowly than a flare's radiation, typically between 90 and 500 miles per second, which means it takes anywhere from 1 to 3 days to reach Earth after leaving the Sun. That travel time is actually useful. It provides warning, time to prepare for the arrival of the disturbance. When a coronal mass ejection reaches Earth, it interacts with Earth's magnetic field. If the magnetic field carried inside the ejected cloud is oriented in a particular way when it arrives, specifically if it points southward and therefore aligns anti-parallel with Earth's northward-pointing magnetic field, the two fields connect in a process called magnetic reconnection. Energy transfers from the solar cloud into Earth's magnetosphere. Charged particles are accelerated and driven into the polar regions. The result is a geomagnetic storm. And depending on the intensity, the consequences range from spectacular auroras at unusually low latitudes to serious disruption of satellite operations, GPS systems, radio communications, and at the extreme end, the induction of currents in long ground-based electrical conductors that can damage or destroy power grid transformers. The Carrington event of 1859 is the reference point for understanding what a truly extreme geomagnetic storm looks like. In early September of that year, a British amateur astronomer named Richard Carrington was sketching sunspots through his telescope when he observed something he had never seen before, a brief, intense brightening in the active region he was observing. Within minutes, the first effects of what was an enormous solar flare reached Earth. About 18 hours later, the associated coronal mass ejection arrived, far faster than typical, because it was traveling through space that had been pre-cleared by an earlier, smaller ejection. The resulting geomagnetic storm was the most powerful in recorded history. Telegraph systems across North America and Europe, the period's most advanced electrical infrastructure, were overwhelmed. Currents induced in the telegraph lines by the geomagnetic disturbance were powerful enough that operators reported receiving painful electric shocks from their equipment. Some lines reportedly transmitted messages entirely on the geomagnetically induced current after their batteries had been disconnected, running on electricity delivered by a storm from the sun. The aurora borealis was visible across the entire continental United States, across Europe, and even in tropical regions close to the equator, places where the northern lights are essentially never seen under normal conditions. Today, the concern about a Carrington-scale event is not about telegraph operators receiving shocks. It is about something considerably harder to repair. Modern power grids rely on large, high-voltage transformers that are expensive to manufacture, take months to over a year to replace, and are not stockpiled in significant quantities anywhere in the world. A severe geomagnetic storm induces what are called geomagnetically induced currents in the long conductors of those grids, currents that the transformers are not designed to handle. Studies of the grid's vulnerability, including a widely cited analysis by the insurance market Lloyd's of London, estimated that a Carrington-class event striking today could cause economic losses in the United States alone running into the trillions of dollars, with power outages potentially lasting months to years in the most affected regions as damaged transformers are slowly replaced. The crucial detail is that events like this happen. The Carrington event was not a once in the history of the solar system anomaly. It was an extreme example of a category of event that occurs with measurable regularity. A less powerful but still significant geomagnetic storm in 1989 knocked out the power grid of the Canadian province of Quebec for 9 hours. A major coronal mass ejection in 2012 was estimated by researchers to be comparable in power to the Carrington event. It missed Earth because it was launched in a direction that didn't intersect our orbit. The margin was not wide. We cannot predict with reliable precision whether a coronal mass ejection will be geo-effective, meaning oriented to cause maximum disruption, until the cloud is almost at Earth. The orientation of the magnetic field embedded in the cloud, the key variable determining how much energy transfers into the magnetosphere, can only be measured by satellites positioned between Earth and the Sun, typically about 1,000,000 miles sunward, which provides warning times measured in 15 minutes to an hour at best. For the power grid, that is not enough time to implement meaningful protective measures across a large system. It is barely enough time to issue an alert. What we are talking about is an event that is not theoretical, that has historical precedent, that could cause cascading failures in the most critical infrastructure of modern civilization, and for which our warning time in the worst-case scenario is measured in minutes rather than months. That is what the star at the center of our solar system is routinely capable of. And the solar activity cycle means that the frequency and intensity of these events rises and falls on an approximately 11-year schedule. We live under a sun that has periods of heightened activity, and during those periods, the probability of a significant geomagnetic event rises accordingly. The sun's magnetic field doesn't just affect events on or near the solar surface. It extends outward through the entire solar system, carried by the solar wind into a structure that shapes the electromagnetic environment of every planet, every moon, and every spacecraft that has ever operated within the heliosphere. As the solar wind streams outward, it carries the sun's magnetic field lines with it, but the sun's rotates, completing one rotation roughly every 25 to 35 days, depending on latitude. Because, unlike Earth, the sun does not rotate as a rigid body. The combination of the outward flow of the solar wind and the rotation of the sun winds those field lines into a spiral pattern, similar to the way water arcing off a rotating garden sprinkler forms curved streams rather than straight ones. This structure is called the Parker spiral, named after the physicist who first described it mathematically, and it fills the entire heliosphere from the sun's surface all the way out to the heliopause. The Parker spiral is not simply a background feature with no practical consequence. It organizes how energetic particles travel through the solar system. Charged particles, including energetic protons from solar flares and cosmic rays entering from outside the heliosphere, tend to follow magnetic field lines rather than traveling in straight lines. The spiral structure of the interplanetary magnetic field therefore influences where particles end up and how quickly they arrive at any given location. A solar flare's energetic particles don't flood the heliosphere uniformly. They flow preferentially along the field lines connecting the eruption site to other parts of the solar system, and whether Earth happens to be well connected to those field lines at the moment of an event determines in part how much particle radiation we receive. Earth's own magnetic field interacts continuously with this interplanetary structure. At the boundary between the two, a region called the magnetopause, the relationship between the solar magnetic field and Earth's field determines how much energy transfers from the solar wind into the magnetosphere. When the interplanetary magnetic field is oriented southward and Earth's field is oriented northward, the two fields meet in an anti-parallel configuration and magnetic reconnection occurs. Energy surges into the magnetosphere. This is the trigger for geomagnetic storms, and it happens not only during dramatic coronal mass ejections, but also during routine encounters with co-rotating interaction regions and during intervals when the background solar wind happens to carry a southward-pointing field component. The sun's magnetic field is also not stable over long periods. Every 11 years, at the peak of the solar activity cycle, the sun's magnetic field undergoes a full reversal. The north and south magnetic poles of the sun swap. During the transition, the field becomes extraordinarily complex. Multiple poles appear simultaneously. The simple dipolar structure that organizes the corona during solar minimum dissolves into a tangled, multipolar configuration that drives more frequent and more intense eruptions. Sunspot numbers peak, flare frequency increases, coronal mass ejections become more common. The solar maximum that peaked around 2024 produced several significant events. Coronal mass ejections reached Earth that generated geomagnetic storms strong enough to produce visible auroras across large portions of the United States and Europe, at latitudes where such displays are normally invisible. No major infrastructure damage resulted, but the events illustrated clearly that the conditions for far more serious outcomes exist and recur. The difference between an event that produces a spectacular aurora and one that damages power grid hardware is a matter of precise timing, of the orientation of the solar magnetic field embedded in the arriving cloud, and of how well connected Earth happens to be to the particular active region that produced the event. Those variables are not under our control and cannot be predicted reliably far in advance. The interplanetary magnetic field also plays a critical role in the radiation environment for any human spaceflight beyond low Earth orbit. Earth's magnetic field provides substantial protection for anyone at the altitudes where the International Space Station operates. Venture beyond it, to the Moon, to Mars, or anywhere in interplanetary space, and the shielding provided by Earth's field disappears. What remains is the solar wind, the interplanetary magnetic field, galactic cosmic rays streaming in from outside the heliosphere, and whatever material the spacecraft and the spacesuit can provide. Solar particle events, the bursts of energetic protons produced during major flares and coronal mass ejections, represent a genuine radiation hazard for astronauts in interplanetary space. A major event without warning and without a properly shielded storm shelter could deliver radiation doses that cause acute radiation syndrome. Astronauts on a Mars transit, months from Earth in either direction, with no way to shelter behind Earth's magnetic field, face a radiation environment that current spacecraft designs have not fully solved. The Sun, in other words, makes the entire inner solar system a radiation environment that is manageable on Earth's surface because of layers of protection we didn't build and can't dismantle, and actively hostile beyond those layers in ways that human spaceflight has not yet fully addressed. What the Sun does today is not what it will do in 1 billion years, or in 5 billion years, or in what the Sun will eventually become. The activity we observe and the threat it poses is a snapshot of a middle-aged star in a particular phase of its evolution, and that evolution is ongoing. Stars on the main sequence, the long, stable period during which they fuse hydrogen in their cores, gradually increase in luminosity over time. As the composition of the core changes, and the core slowly contracts and heats. The Sun has been brightening at a rate of roughly 1% every 100 million years since it formed. That doesn't sound like much, but compounded over billions of years, the effect is substantial. The Sun today is estimated to be approximately 30% more luminous than it was when the solar system first formed, 4.6 billion years ago, and it will continue brightening on that same trajectory going forward. This slow brightening has already left a mark on the history of the inner solar system. It is directly relevant to why Venus looks the way it does today, and it is directly relevant to what will eventually happen to Earth. Earth's climate system has adapted to the gradually brightening Sun through a combination of mechanisms, most notably the long-term carbon cycle, in which plate tectonics plays a central regulatory role. When temperatures rise, chemical weathering of silicate rocks accelerates, drawing carbon dioxide from the atmosphere and depositing it in the oceans and eventually in marine sediments. This negative feedback cools the climate. When temperatures fall, weathering slows, volcanic outgassing continues to add carbon dioxide to the atmosphere, and temperatures rise again. Over hundreds of millions of years, this cycle has helped keep Earth's surface temperatures within a range compatible with liquid water, even as the Sun's output has increased. But the carbon cycle has limits. As the Sun continues to brighten over the next billion years, the rate of increase in solar input will begin to exceed what the carbon cycle can compensate for. Models suggest that in roughly 1 billion years, the Sun will be bright enough that Earth's surface temperatures will begin to rise in a way that accelerates the evaporation of the oceans. Water vapor is itself a potent greenhouse gas. Its increase in the atmosphere drives further warming. More evaporation, more water vapor, further warming still. The feedback spirals until the oceans are gone entirely. The surface of Earth becomes a baked, waterless rock, resembling what Venus looks like today. That is not 1 billion years from now, in some distant, barely imaginable future. It is 1 billion years from now, which is, to be sure, an enormously long time. But complex multicellular life on Earth has only existed for about 600 million years. The amount of time remaining for complex life on Earth's surface before the Sun's brightening makes it uninhabitable is comparable to the entire span of animal evolution to date. One gets the sense of something that is, by the Sun's timetable, already approaching its conclusion. The full end of the story is more dramatic. In roughly 5 billion years, the hydrogen in the solar core will be essentially exhausted. Without the outward pressure of fusion to balance gravity, the core will contract and heat further. This accelerates fusion in a shell surrounding the now inert core, driving a rapid expansion of the sun's outer layers. The sun will swell into a red giant, its radius growing to perhaps 100 to 200 times its current size. Mercury will certainly be swallowed by the expanding sun. Venus very likely as well. What happens to Earth is uncertain, depending primarily on how much mass the sun sheds during its expansion, which affects how Earth's orbit evolves in response to the changing gravitational environment. Some models suggest Earth might migrate outward just far enough to avoid engulfment. Others suggest it will be consumed. Either way, the surface of Earth will be completely sterilized, its oceans long gone, its atmosphere stripped. After the red giant phase, the sun will expel its outer layers as a shell of gas expanding into space, forming what astronomers call a planetary nebula. The core, stripped of those outer layers, will remain as a white dwarf, an object roughly the size of Earth, but containing the sun's mass, incredibly dense, no longer fusing anything, simply radiating stored heat slowly into space over billions of years. The solar system, whatever remains of it by then, will orbit a fading ember for longer than the current age of the universe. All of this is certain, not probable, not likely, certain. The sun's evolution is governed by physics that we understand well, and the physics says this is where the story goes. We live at a particular moment in that story, a moment that is genuinely favorable for life on Earth, but one that exists within a larger timeline that is completely indifferent to that favorability. Two of Earth's three nearest planetary neighbors are uninhabitable in ways that are not incidental. They are uninhabitable for reasons that illuminate how narrow and contingent Earth's habitability actually is, and what happens to rocky planets when the conditions that make Earth livable are absent. Mercury is the innermost planet, the smallest of the eight, and in some ways the simplest story. It essentially has no atmosphere. What thin envelope of gas it once possessed has been almost entirely stripped away by the solar wind over billions of years. Without an atmosphere, there is nothing to moderate temperatures, nothing to distribute heat from the sunlit side to the night side, nothing to slow the swing from one extreme to the other. The sunlit surface of Mercury reaches temperatures of around 800 degrees Fahrenheit, hot enough to melt lead. The night side of Mercury, after a Mercurian night that lasts nearly 3 Earth months because the planet rotates so slowly, drops to approximately 290 degrees below 0 Fahrenheit. The same planet, the same surface, separated by the difference between whether sunlight is hitting it or not, spanning a temperature range exceeding 1,000 degrees. Mercury's surface is, in addition, essentially a museum of early solar system violence. Without plate tectonics, without significant volcanic resurfacing, without wind or water erosion, almost nothing on Mercury has been erased since it was placed there by impacts billions of years ago. Every crater that exists on Mercury today is a record of something that struck it, most of them from the era of intense bombardment early in the solar system's history, when the supply of large impactors was much greater than it is today. The surface is saturated with overlapping craters, some of them ancient enough that they have themselves been cratered by subsequent impacts, which were then cratered by still later events. The record goes back almost to the beginning. Mercury would not be a good place to visit, and an impossible place to live, but it isn't inherently disturbing in the way Venus is. Venus is disturbing because it is almost identical to Earth in basic physical properties, and yet has become a completely different kind of hell. Venus and Earth are sometimes described as twin planets. They are almost exactly the same size, almost the same mass, formed at roughly the same time from the same protoplanetary disk, and orbit at distances from the Sun that are not dramatically different. If you were designing a solar system and wanted two planets with similar prospects, you might draw something like Venus and Earth, and then one of them went on to develop oceans, a moderate climate, and an extraordinary diversity of life, while the other became the most hostile planetary surface in the inner solar system. The surface of Venus bakes at around 860 degrees Fahrenheit, approximately 460 degrees Celsius, a temperature hot enough to glow faintly in the dark. That surface temperature is maintained by an atmosphere that is 96% carbon dioxide, generating a greenhouse effect so intense that Venus is actually hotter than Mercury, despite being nearly twice as far from the Sun. The atmospheric pressure at Venus's surface is about 92 times Earth's atmospheric pressure at sea level, roughly equivalent to the pressure experienced at 3,000 feet below the ocean's surface. The clouds visible from space are not water clouds. They are dense layers of sulfuric acid. The Soviet space program sent a series of spacecraft to Venus between the 1970s and early 1980s, some of which successfully reached the surface and operated for brief periods before being destroyed by the environment. The longest surviving lander, Venera 13, lasted 127 minutes before the combination of heat and pressure ended the mission. The surface images it returned before failing show a barren, rock-strewn landscape illuminated by a dim orange light filtered through the thick atmospheric column above it. Those images are all we have. 127 minutes of survivability on the surface of the planet closest to Earth. Venus almost certainly had liquid water at some point in its early history. The conditions during the early solar system may have allowed surface water to exist on Venus for as long as 2 billion years before conditions changed. What changed was the sun's slow brightening, combined with the absence of the plate tectonic carbon cycling that has kept Earth's climate regulated. As Venus warmed, water vapor entered the atmosphere. Water vapor is a greenhouse gas. This drove further warming, more evaporation, more water vapor. The feedback became self-sustaining. The oceans evaporated. The water vapor in the upper atmosphere was split by ultraviolet radiation into hydrogen and oxygen. The hydrogen escaped to space. The oxygen reacted with surface rocks. The water was gone. Without water cycling through the atmosphere and oceans, the Venus equivalent of the carbon cycle that regulates Earth's temperature collapsed. Carbon dioxide built up from volcanic outgassing with nothing to draw it back down. The greenhouse effect intensified further. The result is what Venus looks like today. This is not just a story about Venus. It is a demonstration that a planet very similar to Earth, starting in a similar position relative to its star, can evolve into something that destroys our best spacecraft in about 2 hours. The line between Earth's outcome and Venus's outcome was not obvious from the beginning. It depended on specific conditions, specific timing, specific feedback loops that went one way rather than another. Earth is not the default outcome for a rocky planet in this region of the solar system. Earth is an exception. Venus is the reminder of what the default looks like. Earth is the only planet we know of that has managed to maintain conditions suitable for complex life over the billions of years that complex life requires to evolve. Understanding why requires understanding which specific factors made it possible, and recognizing that each of them is contingent, not guaranteed. The most foundational protection Earth has is its magnetic field. Generated by convection currents in the liquid iron outer core, Earth's magnetic field extends outward into space, forming a magnetosphere that deflects the solar wind before it can strip away the atmosphere, the way it stripped away Mars's. Without the magnetic field, Earth's atmosphere would gradually erode. Oxygen and water vapor at the upper atmosphere would be ionized by solar radiation, those ions accelerated away by the solar wind, and the atmospheric reservoir would slowly deplete over timescales of hundreds of millions of years. We know this is what happens because we have Mars, which lost its magnetic field, its atmosphere, and eventually its liquid surface water, all in that sequence. The magnetic field is not guaranteed or permanent. It is generated by a heat-driven process in the core, and the core is slowly cooling over geological time. The day will eventually come when the core has cooled enough that convection weakens or stops, and the dynamo that generates the field runs down. On shorter timescales, the field undergoes intermittent reversals in which the north and south magnetic poles swap positions. These reversals don't happen suddenly. The field weakens, grows disorganized and complex, may temporarily develop multiple poles in different locations, and then gradually reestablishes itself in the opposite orientation. During these transitional periods, which can last thousands to tens of thousands of years, the field is weaker than normal and provides reduced protection against the solar wind. How much additional radiation reaches the surface during reversals is a subject of ongoing research. The last complete reversal occurred about 780,000 years ago. Earth's atmosphere provides a second layer of protection, both against radiation and against the constant rain of small objects from space. A rocky object that would survive to reach the ground if it were approaching a body, like the Moon or Mercury, is instead heated by friction with the atmosphere to the point of ablation. The surface material burns away, the object loses mass, and for smaller objects, it can be completely consumed before reaching the surface. This is what we see as meteors, pieces of debris burning up harmlessly at altitude. The same planet that is vulnerable to very large impactors benefits enormously from atmospheric protection against the constant background of smaller objects. The presence of water in liquid form over billions of years is not simply a pleasant feature of Earth. It is a prerequisite for the kind of complex chemistry that life requires, and it requires a very specific combination of circumstances to maintain. Earth's distance from the Sun places it within what is called the habitable zone, the range of distances at which liquid water can potentially exist on a planet's surface given reasonable assumptions about atmospheric composition. But the habitable zone is not a guarantee. Venus was potentially in the habitable zone for billions of years and developed a runaway greenhouse effect anyway. The maintenance of liquid water on Earth over 4 billion years required not just the right distance, but the right atmosphere, the right geological activity, and the right feedback mechanisms to keep temperatures stable. Plate tectonics has been essential. The subduction of oceanic crust, the building of mountains through continental collision, the volcanic outgassing that releases carbon dioxide, all of these processes are part of a planet-wide carbon recycling system that has kept Earth's atmospheric composition and surface temperatures within life-compatible ranges even as the sun slowly brightened. Earth without plate tectonics might still have started with liquid water, but might have developed a runaway greenhouse effect earlier, might have frozen completely during one of the periodic low CO2 intervals that plate tectonics normally prevents. Plate tectonics is not a universal feature of rocky planets. We have no confirmed example of it operating on any other planet in the solar system. Earth may be unusual in having it. All of this together, the magnetic field, the atmosphere, the liquid water, the plate tectonics, the appropriate distance from the sun, amounts to a very specific combination of factors that have operated together over a very long time. Remove any one of them, or alter the timing of when any one of them appeared or changed, and Earth's trajectory might look like Mars or Venus instead. Earth is not the inevitable product of being a rocky planet at the right distance from a stable star. It is an outcome that required multiple things to go right over an enormous span of time. The Moon is the most studied extraterrestrial body in human history. 12 people have walked on it. Hundreds of kilograms of its material have been returned to Earth for analysis. It has been orbited, mapped, bombarded with impactors deliberately to see what the resulting plumes reveal about surface composition, and studied by every conceivable observational technique for decades. And yet one of the most important things about the Moon is something that it represents rather than something it is. A reminder that Earth itself is the product of a catastrophic collision. The leading explanation for the Moon's origin holds that approximately 4.5 billion years ago, when the solar system was still in its turbulent early phase, the proto-Earth was struck by a body roughly the size of Mars. This object, which has been given the name Theia in the scientific literature, is thought to have hit at a relatively oblique angle rather than dead-on. The energy released in this impact was staggering. Material from Theia and from Earth's outer layers was vaporized and blasted into orbit. Over time, some of that material escaped, some fell back to Earth, and a portion coalesced under gravity into the object we now recognize as the Moon. The evidence for this model comes from multiple sources. The Moon's bulk composition is remarkably similar to Earth's mantle material, as you would expect if the Moon formed largely from material ejected from Earth's outer layers by an impact. The Moon is depleted in volatile elements compared to most solar system bodies, consistent with the material having been vaporized in a high-energy impact event, with the volatiles escaping in that vaporization. The lunar samples returned by the Apollo missions have isotopic compositions that are extraordinarily similar to Earth's. Difficult to explain if the Moon formed from a wholly independent body, but consistent with origin from Earth material. And the Moon's large size relative to its host planet is unusual in the solar system. Most large moons around other planets are much smaller relative to their parent body, while Earth and the Moon are almost more like a double planet. The implications of this are worth sitting with. The Moon that stabilizes Earth's axial tilt. that drives the tidal cycles that may have played a role in the evolution of complex life, that provides the tidal forces that have helped regulate Earth's rotation rate over geological time, that lights the night sky and has served as a calendar for every human civilization that has ever existed. That was the destination of the first crewed missions to another world. That object is the wreckage left over from the most violent event Earth has experienced since its formation. We are orbited by a debris field, a large, organized, spherical debris field shaped by gravity into a world with its own geology and its own history, but wreckage nonetheless. The Moon's own surface is a record of the solar system's early violence that Earth's geological processes have largely erased at home. The vast dark plains visible on the Moon, the maria that dominate its near side and give the Moon its recognizable face, are ancient lava flows that filled enormous impact basins. Those basins were formed when objects large enough to punch through the lunar crust struck during the period of intense early bombardment. The South Pole Aitken Basin on the far side is one of the largest confirmed impact structures anywhere in the solar system, roughly 1,600 miles across and about 5 miles deep. A scar so enormous it altered the thermal history of the region. Permanently shadowed craters near the lunar poles hold another kind of record. The floors of these craters have never seen direct sunlight because the crater walls are high enough to block it, and the Moon's axial tilt is small enough that the sun's never rises high enough in the sky to illuminate the floors. In these permanent shadows, temperatures drop to about 370 degrees below 0 Fahrenheit, among the coldest naturally occurring surfaces in the solar system, colder than the surface of Pluto. Those cold traps have preserved water ice that has been accumulating there, delivered by cometary impacts and by solar wind interactions, for billions of years. Ice, sitting in permanent cold darkness, on the same world where the sunlit surface approaches 260 degrees Fahrenheit. The Moon is a place of extraordinary contrasts, and those contrasts tell you something real about how this solar system operates. Mars is the most thoroughly studied planet beyond Earth, and what the accumulated study of Mars reveals is a world that lost something essential. Understanding what Mars lost and how it lost it is one of the clearest demonstrations in the entire solar system of how conditions that seem relatively similar to Earth's can lead to radically different outcomes. Mars today is cold, dry, and thin atmosphered. The average surface temperature is roughly 80 degrees below 0 Fahrenheit, about 62 degrees below 0 Celsius. Though temperatures vary enormously depending on latitude, season, and time of day, ranging from around 70 degrees Fahrenheit in summer at the equator during midday to nearly 200 below 0 in winter at the poles. The atmosphere is thin enough that its surface pressure is less than 1% of Earth's at sea level, too thin to keep liquid water stable on the surface under current conditions. If you poured a glass of water on the Martian surface today, it would simultaneously boil from the low pressure and freeze from the low temperature, sublimating directly into vapor without passing through a liquid phase. And yet the surface of Mars is covered in features that could only have formed in the presence of liquid water. Ancient valley networks, some of them resembling terrestrial river drainage systems in their structure, snake across parts of the Martian highlands. Ancient lakebeds preserve sedimentary deposits. Mineral species that require liquid water for their formation are distributed across wide regions of the surface. The Mars rovers and orbiters have returned evidence that liquid water once flowed, pooled, and chemically altered Martian rocks in environments that could have been habitable for life as we understand it. Mars once had a thicker atmosphere and liquid water on its surface. The question is why it doesn't anymore. The answer is that Mars lost its global magnetic field. Mars's interior cooled and solidified, ending the convective process in a liquid iron core that had generated a planetary-scale magnetic field during the early history of the solar system. Without that field, the solar wind had direct access to the upper atmosphere. Charged particles from the sun collided with atmospheric gas, ionized it, and swept it away into space. The process was slow, measured in geological time, but over hundreds of millions of years and then billions of years, it was relentless. The Martian atmosphere thinned. As it thinned, it became less capable of retaining heat. Temperatures dropped. The surface water froze or evaporated into an increasingly thin atmosphere. The water itself was gradually lost to space or locked into permafrost and polar ice caps. Mars became what it is today, not because of a dramatic, sudden catastrophe, but because of the slow, patient, unceasing work of the solar wind over billions of years. The solar wind didn't need to be in a hurry. It had all the time in the universe, and it used it. The result is a planetary surface that preserves in its geology the record of an earlier, more hospitable era, while the atmosphere that made that era possible has been dispersed into interplanetary space. The lesson Mars teaches is patient and exact. The solar wind is not a dramatic event. It doesn't arrive with the sudden violence of a coronal mass ejection or the flash of a solar flare. It is simply always there, always streaming, always pushing. Given enough time and the absence of a magnetic field to deflect it, it accomplishes what a million solar flares couldn't achieve in the span of a human lifetime. It strips a world bare. Every solid surface in the inner solar system is scarred, and understanding why takes you back to a period in the solar system's early history when the entire inner region was something very different from what it is today. A shooting gallery that operated relentlessly for hundreds of millions of years and from which nothing in its path escaped unmarked. The evidence begins with the moon. The surface of the moon, observed through telescopes since Galileo turned one skyward, is dominated by craters, overlapping craters, craters within craters, ancient basins hundreds of miles across where lava flows subsequently flooded the floors, and then those floors were themselves cratered again by subsequent impacts. The record goes back approximately 3.9 to 4 billion years, to a period when the rate of impacts was dramatically higher than it is today. The same pattern is visible on Mercury, which has essentially no geological process capable of erasing old craters, and so carries the full record in its battered surface. It's visible on Mars in the heavily cratered ancient highland terrain. Even on Venus and Earth, where erosion and geological activity have erased direct surface evidence, the chemical fingerprints of this period survive in ancient rocks. This period is called the Late Heavy Bombardment, and the explanation for why it happened involves one of the most dramatic events in solar system history: the rearrangement of the giant planet orbits. In the first hundreds of millions of years after the solar system formed, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were not in the orbits they occupy today. They formed and settled into positions that, while broadly similar to their current arrangement, were different enough that the long-term gravitational interactions among them were unstable. Computer models developed in the early 2000s, primarily by a group of researchers using an observatory on the French Riviera, and described in a framework called the NICE model, after the city where much of the work was done, show what may have happened next. As the giant planets interacted gravitationally over hundreds of millions of years, Jupiter and Saturn drifted into an orbital resonance with each other, a configuration in which their orbital periods fell into a simple ratio that caused them to repeatedly experience each other's gravity at the same point in their paths. This reinforcement amplified the gravitational influence of both planets on the material surrounding them. The result was gravitational chaos. The ice giants, Uranus and Neptune, were scattered to new, larger orbits. The enormous outer disk of icy material beyond the giant planets was destabilized. Billions of cometary bodies and large rocky objects were flung inward toward the inner solar system. What followed was a sustained, intense bombardment. Objects tens of miles across crashed into the Moon, Mercury, Mars, Venus, and Earth, repeatedly over hundreds of millions of years. The energy deposited by the largest impacts was extraordinary. Craters hundreds of miles in diameter were gouged into the Moon's crust. The impacts created so much heat that they temporarily melted the upper layers of the lunar surface in some regions. On Earth, the largest impacts during this period would have deposited enough energy to vaporize entire bodies of water, not to heat them to boiling and evaporate them over days or weeks, but to flash vaporize them nearly instantaneously from the impact energy, creating clouds of steam that would have taken years to condense back into liquid. Whatever life existed on Earth during the worst of this bombardment, and there is evidence that microbial life existed as early as 3.7 to 4 billion years ago, was living through periods of extraordinary planetary-scale heating, driven by impacts from space. The bombardment did not stop at a well-defined date. It tapered off as the supply of large impactors was gradually depleted. Objects struck planets and were consumed. They fell into the sun. They were ejected from the solar system by gravitational interactions with the outer planets. The remaining supply shrank. Impact rates dropped. By roughly 3.7 to 3.8 billion years ago, the worst was over. But the supply was not exhausted. It was depleted. The solar system still contains billions of objects capable of producing major impacts. The bombardment didn't end. It slowed. There is a concept at the heart of much of what the solar system has done across its history and will do in its future that is worth understanding clearly because it appears repeatedly in almost every chapter of the solar system's most dramatic episodes. It is orbital resonance, and it operates in two modes, one that stabilizes and one that destroys. When two bodies orbiting the same central object have orbital periods that stand in a simple numerical ratio to each other, a 2-to-1 ratio, or a 3-to-2 ratio, or a 4-to-3 ratio, they repeatedly line up with each other in the same part of their orbits. Each time they line up, they exert a gravitational pull on each other. The pull is small, but because it happens in the same part of the orbit every time, the effects accumulate rather than canceling out. Over long periods, this repeated directional nudge can either reinforce the orbital arrangement, keeping it stable, or amplify oscillations in the orbit, driving it to become more and more eccentric until the configuration eventually leads to a collision, an ejection, or a dramatic change in trajectory. Pluto and Neptune are locked in a 3-to-2 resonance. For every 3 times Pluto orbits the Sun, Neptune orbits twice. This means that even though Pluto's orbit crosses Neptune's orbit, the two bodies always meet in a part of their orbits far from the actual crossing point. The resonance protects Pluto from being scattered by Neptune's gravity, and it has done so for billions of years. Without the resonance, Pluto's orbit would be gravitationally chaotic, and it would likely have been ejected from the solar system long ago. The Kirkwood gaps in the asteroid belt are the opposite story. The asteroid belt between Mars and Jupiter contains regions where objects are notably absent, cleared out by orbital resonances with Jupiter. An asteroid whose orbital period falls in a simple ratio to Jupiter's orbital period experiences repeated gravitational tugs from Jupiter that amplify its orbital eccentricity. The orbit gradually stretches. The asteroid begins crossing the orbits of other planets. Eventually, it collides with something, falls into the Sun, or is ejected from the solar system. The Kirkwood gaps are holes carved in the asteroid belt by resonance doing its destabilizing work, and they represent a continuous flow of material being kicked out of stable orbits and redirected. The large-scale rearrangement of the giant planet orbits responsible for the late heavy bombardment was also driven by resonance. Jupiter and Saturn's drift into a 2-to-1 resonance was the trigger that released the energy stored in the gravitational interactions between the giant planets and set off the cascade that flung billions of objects into the inner solar system. And here is the part that connects resonance to the present and future. Computer simulations of the long-term orbital evolution of the inner solar system, extended out over billions of years, reveal something that doesn't fit comfortably with our intuition about a stable, orderly arrangement of planets. Mercury's orbit is currently being slowly influenced by a near resonance with Jupiter. Over billions of years, this interaction could drive Mercury's orbital eccentricity high enough that it eventually intersects with Venus's orbit. In a small fraction of simulated long-term solar system evolutions, this leads to a collision between Mercury and Venus, or to Mercury falling into the Sun, or even, in the most extreme cases, to a cascade of orbital instability that eventually involves the Earth and Venus as well. The probability of any of these outcomes over the next 5 billion years is low. Most simulations produce a solar system that remains essentially stable until the Sun exhausts its hydrogen supply. But most is not all. The mechanism for catastrophe is not hypothetical. It is running right now in the gravitational interactions that occur every time the planets complete their orbits. The outcome is genuinely uncertain over sufficiently long timescales because the system is chaotic in the technical, mathematical sense. Tiny differences in current positions and velocities grow exponentially over time, making long-range prediction impossible. We live in a system that is stable on human timescales, stable on civilizational timescales, broadly stable on geological timescales, but not stable in the absolute permanent sense that the word stable typically implies. Between the orbits of Mars and Jupiter lies a region of the solar system that popular culture has long imagined as a dense, hazardous obstacle course, the kind of thing that makes interplanetary pilots nervous, with rocks tumbling past in every direction. That image, inherited from science fiction and occasionally from overly dramatic educational media, doesn't correspond to reality. The actual asteroid belt is mostly empty space, and a spacecraft traveling through it is statistically unlikely to come within thousands of miles of any sizable object. But the asteroid belt's lack of crowdedness is not reassuring once you understand what it actually is and what it does. The asteroid belt spans a region from roughly 205 million miles from the Sun to approximately 300 million miles out, between the orbits of Mars and Jupiter. It contains millions of rocky and metallic objects ranging from tiny pebbles to the dwarf planet Ceres, which has a diameter of about 585 miles and accounts for roughly a third of the entire mass of the belt. The total mass of all asteroid belt material combined is only about 4% of the mass of the Moon. That's modest. What is not modest is the rate at which Jupiter's gravity continuously manipulates the orbits of objects within that belt. Jupiter's gravitational influence on the asteroid belt creates regions of instability called Kirkwood gaps. Objects that drift into these gap regions find their orbits being amplified by repeated gravitational tugs from Jupiter until their eccentricities increase enough to put them on new trajectories. Some of those new trajectories carry them inward, into the inner solar system, where they can eventually become Earth-crossing objects. Jupiter is, in this sense, continuously loading a gravitational catapult and flinging a fraction of the asteroid belt's contents toward the rocky planets. But Jupiter's influence doesn't work alone. A subtler mechanism called the Yarkovsky effect operates in parallel, slowly and continuously nudging asteroid orbits through an unexpected mechanism: the re-radiation of sunlight as heat. When sunlight strikes an asteroid's surface, it warms the rock. As the asteroid rotates, the warmed surface eventually rotates away from the sun and faces into open space, where it radiates that absorbed heat as infrared radiation. Because radiation carries momentum, this heat emission creates a tiny but real force on the asteroid. The direction of this force depends on the asteroid's rotation, and its net effect over millions of years is to very gradually shift the asteroid along its orbit, either expanding the orbit or shrinking it. Given enough time, this tiny force can push an asteroid from a stable orbit into a Kirkwood gap, where Jupiter then takes over and dramatically amplifies the resulting disruption. The Yarkovsky effect has been directly measured for a small number of individual asteroids, confirming that it operates as described. Its significance is that the population of asteroids on Earth-crossing trajectories is not simply depleting as those objects are removed by collisions or gravitational ejection. It is being continuously replenished by fresh material nudged out of stable orbits in the belt. The source of potentially hazardous impactors is not running down. It is being restocked by physics that operates steadily, invisibly, and without pause. There are currently more than 33,000 known near-Earth objects, asteroids and comets, whose orbits bring them into the inner solar system within a region that overlaps with or closely approaches Earth's orbital path. Of those, more than 2,300 are classified as potentially hazardous, meaning they are larger than about 460 feet across and travel on orbits that could bring them within a threatening distance of Earth. These are known objects. The inventory of unknown ones is where the real uncertainty lives. The Chicxulub impactor, the asteroid responsible for the mass extinction that ended the Cretaceous period 66 million years ago, and eliminated the non-avian dinosaurs along with approximately 75% of all species then alive, was estimated at roughly 6 miles across. It struck what is now the Yucatan Peninsula of Mexico at high velocity. The energy released in the impact was approximately 1 billion times that of the atomic bomb detonated over Hiroshima. The crater it formed is more than 100 miles across and is buried under sediment and ocean water, but remains clearly identifiable in geological surveys. The immediate destruction was catastrophic. But what followed the impact may have been worse than the impact itself. The collision vaporized enormous quantities of rock, including sulfate-rich sedimentary material at the impact site, releasing sulfur dioxide into the stratosphere. Wildfires ignited across wide regions. Soot from those fires, combined with mineral dust and sulfate aerosols, blasted into the upper atmosphere, blocked sunlight from reaching the surface. Global temperatures plunged. Photosynthesis collapsed across most of the planet. Food chains broke down at their base. Marine ecosystems were devastated, as ocean chemistry was disrupted by the atmospheric acid rain. The darkness and cold persisted for years. The non-avian dinosaurs, which had dominated terrestrial ecosystems for more than 160 million years, were gone. What replaced them was us, eventually. The extinction of the dinosaurs cleared ecological space that mammals then expanded into, leading over tens of millions of years to the emergence of primates, then hominids, then Homo sapiens. We exist in part because something roughly 6 miles across arrived from space 66 million years ago. That fact has a quality to it that is difficult to absorb without a certain vertigo. In 2013, a rocky object estimated at about 65 feet across entered Earth's atmosphere over Chelyabinsk, Russia. It produced no warning whatsoever. Ground-based telescopes could not see it in the days before its arrival because it was approaching from roughly the direction of the sun, a blind spot that existing survey systems cannot cover effectively. The object exploded at high altitude in the atmosphere, producing an airburst with an energy equivalent to roughly 30 times the Hiroshima bomb. The shockwave traveled outward at the speed of sound, shattering windows across a wide area of the city and surrounding region. About 1,500 people were injured, primarily from flying glass. Had the object been twice as large, or had it arrived at a different angle that didn't distribute the explosion across as wide an area, the casualties would have been dramatically different. 5 years before Chelyabinsk, in 2008, a small asteroid was detected a short time before it struck Earth's atmosphere over Sudan. That detection, while brief, was a first. The first time an asteroid had been positively identified before impacting. The Chelyabinsk impactor was not detected at all. The survey of the near-Earth object population is ongoing, but remains incomplete, particularly for objects in the 50 to 500 foot size range that are large enough to cause regional destruction but small enough to have escaped systematic detection by current telescopes. The DART mission, launched in 2021 and concluding with an intentional collision with the small asteroid Dimorphos in September 2022, changed the asteroid's orbital period around its companion Didymos by a measurable amount, confirming that the kinetic impactor technique, crashing a spacecraft into an asteroid to alter its trajectory, works as a planetary defense strategy. That is genuinely significant. For the first time in history, a species on Earth deliberately changed the motion of a natural body in the solar system. The limitations of the technique are equally important to understand. It requires the target object to be identified far enough in advance to plan and execute a mission, which means years of lead time at minimum. It is most effective for objects on well-characterized orbits where a small, early trajectory change prevents a future impact. For objects discovered late, for objects arriving from the direction of the sun where our survey capability is weakest, for objects whose composition makes them respond differently to kinetic impact than expected, the window for effective intervention narrows dramatically. Planetary defense works best as a long-term surveillance and early warning system. As a last resort emergency measure, its reliability decreases rapidly. The lesson of the asteroid belt, the Yarkovsky effect, and the incomplete near-Earth object inventory is that the threat from space is not a single, dramatic, easily categorized event lurking somewhere in the distant future. It is a continuous, statistical reality operating across a wide range of object sizes, time scales, and probability levels. At the low end of the size range, objects capable of producing local to regional destruction arrive on timescales of decades to centuries. At the large end, events capable of mass extinction are rarer but have definite historical precedent. Cross the asteroid belt and the solar system changes character entirely. The 4 inner rocky planets operate at scales and temperatures that, while extreme compared to everyday human experience, are at least comprehensible in basic terms. Jupiter operates on a different set of scales altogether, in a different physical regime, and with a presence in the solar system so dominant that its effects are felt everywhere. Jupiter is the largest planet in the solar system. Its diameter of roughly 88,800 miles makes it about 11 times wider than Earth. Its mass of about 318 Earth masses makes it more than twice as massive as all the other planets in the solar system combined. It has no solid surface. descend through its outer atmosphere of hydrogen and helium gas, and the pressure increases steadily until the gas transitions into a liquid and then, at greater depths, into a state called metallic hydrogen, where the pressure is so extreme that hydrogen's electrons are torn loose from their atoms and move freely through the material, making it electrically conductive like a metal. The core of Jupiter, if it has a distinct core, is buried under many thousands of miles of crushing liquid and metallic hydrogen. Jupiter's metallic hydrogen interior drives its magnetic field. That field is approximately 20,000 times stronger than Earth's magnetic field, and the magnetosphere it generates extends an extraordinary distance into space. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear several times the width of the full moon, despite Jupiter being hundreds of millions of miles away. The space inside this magnetosphere is one of the most intensely radioactive environments in the solar system. The reason is partly Jupiter's own dynamics and partly its moon Io. Io, the innermost of Jupiter's 4 large Galilean moons, is the most volcanically active body known anywhere in the solar system. Its extraordinary volcanism is driven by tidal heating, the constant flexing of Io's interior by the competing gravitational pulls of Jupiter and the other Galilean moons. Io has hundreds of active volcanic centers. Some of its eruption plumes reach altitudes of more than 300 miles above the surface, was higher than any terrestrial volcanic plume. The surface of Io is continuously renewed by flows of sulfurous lava and volcanic deposits, erasing craters as fast as the occasional impactor creates them. There are essentially no impact craters visible on Io's surface. The volcanic resurfacing rate is high enough to erase them. All of this volcanism pumps enormous quantities of material into Jupiter's magnetosphere. Sulfur dioxide and other volcanic gases are injected into the magnetic environment, ionized by radiation and particle collisions, and trapped in a vast ring of plasma called the Io plasma torus that orbits Jupiter in the region of Io's orbit. The result is a particle radiation environment in Jupiter's inner magnetosphere of extraordinary intensity. A human being exposed to the radiation in Jupiter's inner magnetosphere without shielding would receive a lethal dose within minutes. The electronics of an unshielded spacecraft would begin failing within hours. The Juno spacecraft, which entered Jupiter orbit in 2016, carries its most sensitive electronics inside a titanium radiation vault, specifically designed to attenuate the particle radiation environment. Even with this protection, the accumulated radiation dose over the mission has been significant. Europa, one of the most scientifically compelling destinations in the solar system, because of the liquid water ocean beneath its icy surface, sits within the most intense part of Jupiter's radiation belts. Designing a spacecraft that can operate in that environment long enough to meaningfully study Europa is among the most technically demanding challenges in planetary science. NASA's Europa Clipper mission, launched in 2024, is designed to make repeated brief flybys rather than entering orbit around Europa, specifically to limit radiation exposure during the mission. The Great Red Spot on Jupiter, the enormous anticyclonic storm that has been continuously observed for at least 350 years, has been larger than Earth for essentially its entire documented history, though it has been slowly shrinking over the past century. Lightning within Jupiter's atmosphere occurs at energy levels that make terrestrial thunderstorms look trivial, with individual discharge. Events estimated at some of the highest intensities measured anywhere in the solar system. Jupiter's atmosphere contains no reference point for a ground-level observer because there is no ground level. It is a planet of atmosphere all the way down. In July 1994, astronomers observed Comet Shoemaker-Levy 9, a comet that had been gravitationally captured by Jupiter and broken into roughly 21 fragments by tidal forces during a previous close approach, fall into Jupiter over 6 days. Each fragment struck the planet in sequence, and each impact left a dark scar in Jupiter's atmosphere, larger than the diameter of Earth. The energy released per fragment was estimated at millions of megatons. The combined energy release over the course of the week was a demonstration at planetary scale of what happens when even moderately large objects collide with large bodies. It was also the first time in human history that a collision event in the solar system was predicted in advance and observed directly as it happened. If Jupiter is the solar system's most extreme planet, Saturn produces arguably the most visually striking feature. a ring system so geometrically perfect and visually distinctive that it has appeared in virtually every artistic depiction of the solar system since telescopes first resolved it in the 17th century. What the rings actually are, understood in full physical terms, is somewhat different from beautiful. Saturn's main ring system extends from roughly 4,200 miles above Saturn's equator out to approximately 82,000 miles, a width of tens of thousands of miles. The rings are composed primarily of water ice, with contributions from rocky material, and the particles making up the rings range from grains of dust to chunks of ice and rock as large as a house. All of this material orbits Saturn independently, each piece following its own orbit governed by Kepler's laws. What makes the rings astonishing is how thin they are. The main rings, despite spanning tens of thousands of miles in width, are in most places between 30 and 300 feet thick. If you scaled the ring system down until its width equaled the width of a standard piece of paper, the rings would be thinner than a single atom. They are, on the scale of their own diameter, among the flattest structures in the solar system. The rings are not static. Material within them is constantly colliding with other material, breaking apart into smaller fragments or sticking together temporarily into clumps. The boundary between different rings is maintained by shepherd moons, small satellites whose gravity herds ring particles and prevents them from spreading. These shepherd moons trace the edges of distinct ring divisions with surprising precision. The Cassini division, the most prominent gap between the main rings visible even through a small telescope, is cleared by a gravitational resonance with the moon Mimas, which orbits at a distance such that particles at the Cassini division's location complete exactly 2 orbits for every one of Mimas's. The Cassini spacecraft, which orbited Saturn from 2004 to 2017 and provided the most detailed study of the Saturnian system yet achieved, discovered that the rings are losing mass at a rate driven by a process called ring rain. Ring material from the inner edges of the rings is dragged inward by interactions with Saturn's magnetic field and falls into the upper atmosphere as a continuous shower. Estimates based on Cassini's data suggested that ring material is being lost at a rate of up to roughly 10,000 kilograms per second. At that rate, the rings as they exist today would disappear completely within 100 to 300 million years. In geological terms, that is relatively soon. The solar system is 4.6 billion years old. The rings will be gone in, at most, a few % of that remaining time. Anyone looking at Saturn in 200 million years may be looking at a planet that has shed its most distinctive feature. The rings of Saturn are a temporary structure, visible at this particular moment in the solar system's history because we happen to exist within the brief window when they are present. What are the rings at their origin? Almost certainly the remains of something destroyed. The most widely accepted hypothesis holds that the rings represent material from a moon or a comet that either wandered too close to Saturn and was torn apart by tidal forces or was shattered by a large collision. Saturn's gravity, at the distances corresponding to the ring system, generates tidal forces strong enough to prevent loose material from assembling into a single body. Any satellite or large comet that crosses this threshold, called the Roche limit, is pulled apart into fragments that then spread into a disk around the planet. The beautiful mathematical perfection of Saturn's ring plane is the organized wreckage of something that was destroyed. Every outer planet has rings, which means every outer planet has at least one record of something catastrophically disrupted. Saturn's collection of moons includes some of the most scientifically compelling worlds in the solar system, 2 of them in ways that have fundamentally changed how scientists think about the possibility of life beyond Earth. Titan, Saturn's largest moon, is unique in the solar system for carrying a dense nitrogen-rich atmosphere with surface pressure about 1.5 times Earth's. This atmosphere, combined with Titan's surface temperature of roughly 290 degrees below 0 Fahrenheit, creates conditions in which methane plays the role that water plays on Earth. Methane exists on Titan's surface as a liquid. It evaporates from those liquid bodies, forms clouds, rains back down, carves river channels, and collects in lakes and seas. The Cassini mission and the Huygens probe, which descended through Titan's atmosphere in 2005 and returned the first images from its surface, revealed a world with orange dunes made of organic particles, river channels eroded by methane, and large, smooth seas of liquid methane near the poles. The atmosphere itself is chemically complex in ways that are directly relevant to questions about life. Ultraviolet radiation from the sun drives reactions in Titan's upper atmosphere that produce a rich variety of organic molecules, substances that descend through the atmosphere and accumulate on the surface. These molecules are sometimes described as tholins, a class of complex organic compounds whose chemistry is in some ways analogous to the prebiotic chemistry thought to have existed on early Earth before life arose. Titan is running a version of early Earth chemistry at cryogenic temperatures. Whether that chemistry leads anywhere, whether life could exist in liquid methane as a solvent in the way that Earth's life uses liquid water, is genuinely unknown. Enceladus is a different story, and in some ways more immediately striking. It is a small moon, only about 313 miles across, whose surface temperature is cold enough to place it among the coldest surfaces in the solar system. And yet the Cassini spacecraft discovered that Enceladus has active geysers erupting from its south polar region, plumes of water vapor and ice particles shooting hundreds of miles above the surface into space. The plumes originate from a subsurface liquid water ocean kept from freezing by tidal heating from Saturn's gravity. The same basic mechanism that makes Io volcanic makes Enceladus wet. Cassini flew directly through these plumes and analyzed their composition. It found water, ice, organic molecules ranging from simple compounds to complex ones, and most significantly, molecular hydrogen. Molecular hydrogen in this context is significant because the specific geochemical process that produces it, a reaction between hot water and rock called serpentinization, is the same process that occurs at hydrothermal vents in Earth's deep oceans. Those vents on Earth, completely isolated from sunlight and deriving all their energy from chemical reactions between hot rock and seawater, support entire ecosystems ranging from bacteria and archaea at the base of the food chain to tube worms, crabs, and fish at the top. Life at Earth's hydrothermal vents doesn't need the sun. It runs on chemical energy alone. Enceladus appears to have liquid water, organic molecules, and a hydrothermal system at the floor of its ocean, all three of the key ingredients for the kind of life that thrives at Earth's deep-sea vents. We have not found life in Enceladus's ocean. We have not looked. The instruments on Cassini were not designed for biosignature detection, but the case that Enceladus is one of the most promising places in the solar system to search for life right now, not in some distant theoretical future, but in the existing inventory of solar system objects, is compelling enough that it features prominently in every serious scientific discussion of astrobiology in the outer solar system. The two ice giants represent the least explored category of planet in the solar system. Only one spacecraft, Voyager 2, has ever visited either of them, and those visits were brief flybys with no ability to linger, study in depth, or revisit. What Voyager 2 found during those fleeting encounters was enough to confirm that both planets operate under conditions far outside anything in ordinary human experience. Uranus is geometrically odd in a way that tells you immediately something unusual happened to it. Its axis of rotation is tilted roughly 98 degrees relative to its orbital plane, meaning it orbits the Sun nearly lying on its side compared to the other planets. Earth's axial tilt of about 23 degrees gives us our 4 seasons as each hemisphere alternately tilts toward and away from the Sun. Uranus's extreme tilt means that each pole alternately points almost directly at the Sun for about 21 years and then sits in complete darkness for the following 21 years, in a cycle that plays out over the planet's 84-year orbital period. The seasonal extremes on Uranus are unlike anything in the inner solar system. The most widely accepted explanation for this tilt is a collision. Something large, possibly several times Earth's mass, struck Uranus early in the solar system's history and knocked the entire planet onto its side. The impact also produced Uranus's ring system and shaped the configuration of its moons. Uranus's orientation is a monument to an ancient catastrophe. We see only the aftermath, encoded in the geometry of how the planet moves through space. Neptune, the most distant planet, holds a record for atmospheric violence. Wind speeds on Neptune have been measured at approximately 1,200 miles per hour, roughly 1.5 times the speed of sound in Earth's atmosphere, making them the fastest sustained winds measured on any planet. The Great Dark Spot observed by Voyager 2 in 1989, a storm comparable in scale to Jupiter's Great Red Spot, was Earth-sized and rotating at extraordinary speed. When the Hubble Space Telescope imaged Neptune in the 1990s, the original Great Dark Spot had disappeared, and new storm systems had formed in its place. Neptune's atmosphere is, at least compared to Uranus's relatively featureless cloud deck, surprisingly dynamic for a planet receiving so little solar energy. Neptune's internal heat source is the explanation. Neptune radiates roughly 2.5 times as much energy as it receives from the Sun, implying a significant internal heat source left over from the planet's formation that has not dissipated over 4.5 billion years. That internal energy drives the atmospheric dynamics. Uranus, by comparison, radiates almost no more energy than it receives, suggesting its internal heat has been lost, possibly disrupted by the same giant impact that tilted the planet. Current models of conditions deep within Neptune and Uranus suggest something that sounds like pure science fiction, but is supported by laboratory experiments. At the extreme pressures in the deep interior of these planets, carbon, the element abundant in the ice mixture that makes up a large fraction of both planets, may undergo a phase transition. Under conditions replicating these extreme pressures in laboratory experiments using laser-driven shocks, carbon has been shown to form diamond. In the deep interiors of Neptune and Uranus, diamonds may be continuously raining downward toward the core. It is not a feature that can be directly observed, but the physics support it, and the laboratory experiments back it up. Diamond rain on worlds nearly 3 billion miles from the Sun. Beyond Neptune, the solar system continues with a broad disk of icy material that extends from roughly 2.8 billion miles from the Sun out to approximately 4.6 billion miles, the Kuiper Belt. This region was largely unknown before 1992, when the first Kuiper Belt object beyond Pluto was directly confirmed. Since then, thousands more have been found, and the Kuiper Belt is now understood to be an enormous reservoir of icy bodies, ranging from small fragments to dwarf planets, that represents the outer boundary of the solar system's primordial disk. Pluto, reclassified as a dwarf planet in 2006 when it became clear that it shares the Kuiper Belt with hundreds of similar objects rather than standing alone as a unique planet, has a diameter of about 1,477 miles. The New Horizons flyby in 2015 revealed a world of unexpected geological complexity, with nitrogen glaciers, a large heart-shaped nitrogen ice plain, mountains of water ice reaching several miles in height, and evidence of ongoing geological activity driven by the slow settling of nitrogen ice layers. Pluto is not the dead, featureless ball of ice that many expected. It is a geologically active world, operating at temperatures approaching -380 degrees Fahrenheit, driven by processes that don't require the kind of tidal heating or internal radioactive heat that powers activity closer to the Sun. The Kuiper Belt is not a stable reservoir sitting quietly at the solar system's edge. It is continuously being perturbed by Neptune's gravity. Objects that drift into resonances with Neptune can have their orbits destabilized and changed. Some are redirected outward, eventually escaping the solar system. Others are nudged inward, beginning a slow transition toward the inner solar system. This is where the centaurs enter the story. Most people have never heard of them, but they represent an important and underappreciated aspect of the solar system's ongoing dynamics. Centaurs are bodies orbiting primarily in the outer solar system, between Jupiter and Neptune, whose orbits are gravitationally unstable on timescales of millions to tens of millions of years. They are not stable residents of the outer solar system. They are objects in transition. Most centaurs began their existence as Kuiper Belt objects. Interactions with Neptune's gravity altered their orbits, shifting them inward into the region between the outer planets. In this new territory, they are subject to gravitational influences from all 4 giant planets simultaneously, and their orbits continue to evolve. Some centaurs will eventually be ejected from the solar system. Some will fall into the Sun, and some will be redirected into the inner solar system, where they will heat up as they approach the Sun, develop cometary activity as volatile ices sublimate from their surfaces, and become active comets. Chiron, the first centaur discovered, is roughly 150 miles across and already shows intermittent cometary activity at its current location beyond Saturn. The Centaur population is effectively a pipeline, carrying material from the Kuiper Belt into the inner solar system, with a throughput measured on timescales of millions of years. The supply side of that pipeline is the Kuiper Belt, continuously losing material to Neptune's gravitational influence. The receiving end is the inner solar system. The flow is not random. It is driven by the same orbital mechanics, the same resonances, the same gravitational dynamics that have governed the solar system since the beginning. It continues now, invisibly, at a pace invisible on human team scales, but real and consequential when considered over geological time. Short-period comets, those with orbital periods of less than 200 years, are generally understood to be the products of this pipeline. Kuiper Belt objects redirected through the Centaur population into the inner solar system. Every short-period comet visible from Earth is a piece of material that originated in the outer solar system and made its way inward through the Kuiper Belt to Centaur orbit to inner solar system comet on a journey that took millions of years. The interplanetary medium through which all of this material travels is also not empty in the sense that truly empty means. It is filled with a fine distribution of dust particles shed by comets as they evaporate near the Sun and generated by collisions among asteroids and Kuiper Belt objects. This dust, called the zodiacal cloud, forms a flattened disk aligned with the solar system's orbital plane and scatters sunlight in a way that produces the zodiacal light, a faint pyramid of illumination visible along the ecliptic on clear, dark nights. Earth sweeps up roughly 40,000 tons of this extraterrestrial material every year, most of it arriving as invisible microparticles and micrometeorites, tiny spherical droplets formed when small objects were heated to melting by atmospheric entry. Scientists collect these micrometeorites from Antarctic ice and from high-altitude air samples. They are free samples from the solar system's outer regions, arriving constantly at Earth's surface. Beyond the Kuiper Belt, the solar system enters a domain so distant and so cold that it is nearly impossible to conceptualize. The Oort cloud is thought to begin at roughly 2,000 times the Earth-Sun distance and extend outward to somewhere between 50,000 and 100,000 times that distance. The outer edge of the Oort cloud is, in terms of distance from the Sun, nearly halfway to the nearest star. At those distances, the Sun is not a warm, bright presence. It is simply the brightest point of light in a sky full of them. The Oort cloud is estimated to contain something on the order of 2 trillion icy objects, rocky, ice-rich bodies that have been in these distant orbits for most of the solar system's history, moving so slowly and orbiting so far from the Sun that a single orbit can take millions of years to complete. They exist at temperatures approaching absolute zero. They have not been heated by the Sun in billions of years. They preserve within their composition a record of the conditions present during the solar system's formation, frozen into permanence by the cold of deep space, and they are not beyond reach. The gravitational field that holds these distant objects in their barely moving orbits is weak, because those objects are so far from the Sun that its gravitational grip is correspondingly faint. What this means is that comparatively small perturbations can shift those orbits. A passing star, the gravitational gradient produced by the structure of the Milky Way, the tidal forces from the galactic disk, any of these can alter an Oort cloud object's orbit enough to start it falling inward. The journey takes millions of years, but it ends in the inner solar system, where the newly arrived object heats up as sunlight increasingly reaches it, develops a coma and a tail, and becomes a long-period comet. Long-period comets, those with orbital periods of more than 200 years and often far more, represent one of the more unsettling categories of potential impactors in the solar system. Unlike near-Earth asteroids, which have been tracked for years or decades and whose orbits can be predicted with precision, long-period comets arrive from the Oort cloud, having never previously passed through the inner solar system. They are falling in for the first time. They have never been heated by the Sun. They can be extraordinarily bright and active, releasing vast quantities of volatile gas and dust as they approach. But their orbits, when first detected, may provide only months of warning before closest approach to Earth. The galactic tidal force is not a rare or exceptional event. The Milky Way has a gravitational structure that exerts a continuous tidal influence on the outer solar system, and as the solar system orbits the galactic center at roughly 500,000 miles per hour, completing one galactic orbit every 225 to 250 million years, it passes through different regions of the galaxy with different densities of interstellar gas and dust, and different numbers of nearby stars. This changes the galactic tidal forces on the Oort's cloud over time. During parts of the solar system's galactic orbit, particularly when it passes through the denser regions of the galactic plane in its oscillation above and below the midplane on a cycle of roughly 30 to 35 million years, enhanced tidal forces perturb more Oort cloud objects and send more comets falling inward. Some researchers have proposed that the geological record of mass extinctions on Earth shows a rough periodicity that might be connected to this galactic oscillation cycle. The evidence is controversial and the statistical case is not settled, but the underlying mechanism is real and not disputed. The solar system is not an isolated system. It is embedded in the galaxy, and the galaxy's structure affects what happens at the solar system's outermost edges. Stars occasionally pass close enough to the solar system to significantly perturb the Oort cloud directly. In 2014, astronomers determined from archival observational data that a red dwarf star called Schultz's star passed within about 0.8 light-years of the Sun approximately 70,000 years ago. That placed it within the outer Oort cloud. The encounter was too slow and too distant to have triggered an immediate comet shower, but it would have shifted orbits that are still slowly working their way inward as a consequence. In 2017, astronomers detected something that had never been seen before, an object moving through the solar system on a hyperbolic trajectory that could only be explained if it had originated outside the solar system entirely. It was named Oumuamua, and it was unlike any solar system object previously cataloged. It was apparently highly elongated, possibly disc-shaped or cigar-shaped. It tumbled as it traveled. As it departed the solar system, it accelerated in a way that could not be accounted for by gravity alone. The most plausible explanation, though not universally agreed upon, is that the acceleration was driven by radiation pressure from sunlight acting on a thin, flat object with an unusually high surface area-to-mass ratio, essentially a naturally formed solar sail. In 2019, a second interstellar object was detected, this one named Borisov, and clearly identifiable as a comet, releasing gas and dust as it passed near the Sun. Its composition, where it could be measured, appeared broadly similar to comets from our own solar system, suggesting that some aspects of cometary composition may be common across different planetary systems. The detection of interstellar objects passing through the solar system confirmed something that orbital dynamics had long predicted. Material ejected from other planetary systems during the violent early phases of their formation travels through interstellar space and occasionally passes through our own system. The solar system is not a sealed environment. It has always been porous to material from beyond it, and presumably, material ejected from our own solar system during its turbulent early history is now traveling through the space between other stars, possibly passing through other planetary systems. Pieces of our solar system's history are out there in the interstellar medium, and pieces of other systems' histories have already visited ours. The proposal known as Planet 9, circulating among planetary scientists for about a decade, adds one more layer of uncertainty to our picture of the outer solar system. A handful of extreme trans-Neptunian objects, Kuiper belt bodies in very large, elongated orbits, have their orbital planes clustered together in a statistical alignment that appears unlikely to be coincidental. The most compelling explanation is that a massive undiscovered planet is gravitationally shepherding these objects into their common alignment. Calculations suggest the hypothetical planet would need to be roughly 5 to 10 times Earth's mass, orbiting at somewhere between 400 and 800 times Earth's sun distance, on an orbit taking between 10,000 and 20,000 years to complete. If Planet 9 exists, it has never completed a single orbit during the entire history of human civilization. At its estimated distance, it would be extraordinarily faint, and easily lost against the background of stars in any survey that wasn't specifically targeting the right patch of sky with adequate depth. It may be a planet formed in the inner solar system and ejected outward by early interactions with Jupiter or Saturn. It may be a planet captured from another star during the brief period when the Sun was still embedded in the cluster in which it formed. Or, the statistical clustering of trans-Neptunian orbits may be a measurement artifact, An artifact of the survey biases that cause us to observe some parts of the sky more thoroughly than others, creating the appearance of clustering where none actually exists. We do not know. That is the current state of the science. We may have a planet larger than Earth orbiting in our own solar system that we simply haven't noticed yet, because it's so far away and so faint that none of our existing surveys have found it. The solar system has not finished revealing what it contains. Step back from everything. From the termination shock where the solar wind finally stops, from the Oort cloud's 2 trillion frozen sentinels, from the diamond rain inside Neptune, from Europa's hidden ocean, from the sulfurous volcanoes of Io, from Saturn's temporary rings, from the Chicxulub scar still buried beneath the Gulf of Mexico, from the storm on Jupiter that has been raging since before anyone on Earth had a telescope to observe it. Step back from all of it and look at the whole thing at once. The solar system is approximately 4.6 billion years old. It formed from a collapsing cloud of gas and dust that was itself composed partly of material forged in stars that existed before the sun, stars that lived their full lives and ended, scattering their products into space where they eventually became part of the cloud that became this solar system. The iron in Earth's core passed through the interior of a massive star before the sun existed. The calcium in your bones was manufactured in stellar nuclear furnaces. The oxygen you are breathing right now was produced by stars that died before our solar system was born. The solar system spent its first hundreds of millions of years in a state of orbital chaos, during which the giant planets migrated to new positions, and the inner solar system was subjected to a bombardment so intense that the oceans may have been temporarily vaporized. Life on Earth arose during or shortly after this bombardment. Whatever life existed then survived conditions that we would consider completely incompatible with survival. Since then, the solar system has settled into what we call a relatively stable period, relative to what came before. Not absolutely stable, not permanently stable. The asteroid belt continues to deliver fresh material to inner solar system crossing orbits through the Yarkovsky effect and Kirkwood gap resonances. The Kuiper belt continues to supply centaurs that will eventually become comets. The Oort cloud continues to respond to galactic tidal forces and occasional stellar encounters, sending long-period comets into the inner solar system with minimal warning. The sun continues its slow brightening that will eventually end the possibility of complex life on Earth's surface. Mercury's orbital eccentricity continues to be slowly shaped by resonance with Jupiter in a way that produces, in a small fraction of simulations, catastrophic inner solar system destabilization billions of years from now. And yet, here we are, on a rocky planet at the right distance from a middle-aged star, protected by a magnetic field generated by a convecting iron core, shielded by a shallow ocean of air, stabilized in our axial tilt by a large moon born from the debris of a catastrophic ancient impact, regulated in our long-term climate by a planetary carbon cycle driven by plate tectonics, orbiting in a solar system where the largest planet has a nearly circular orbit and stays in the outer solar system rather than sweeping through the inner one. None of those conditions are guaranteed. None of them are permanent. All of them are contingent, the products of specific early solar system events, specific gravitational interactions, specific geological processes operating over specific timescales. Change any one of them significantly, or alter when it appeared, and the outcome might look like Venus or Mars. Change several of them, and the outcome might not include a habitable planet at all. We exist at a particular moment in the history of a particular solar system, a moment that happens to allow, just barely and with considerable precariousness, the existence of a species capable of understanding the environment it lives in. That species has, in the span of a few decades, mapped the near-Earth asteroid population, sent spacecraft to every planet, detected and characterized the interstellar medium, discovered oceans under the ice of distant moons, and deliberately altered the orbit of an asteroid for the first time in the solar system's history. The solar system is not safe. It never was. It is violent, extreme, and operating on timescales and at energies that dwarf anything in ordinary human experience. The diagram with its neat circles and evenly spaced planets is a convenience, not a description. The description is a thermonuclear star continuously bombarding everything within 11 billion miles with radiation and energetic particles. billions of rocky and icy projectiles on orbits that cross or approach ours. A history written in mass extinctions and crater-saturated surfaces. Neighboring planets demonstrating what happens when the conditions for habitability fail. An outer solar system that continues, on geological timescales, to direct new objects toward the inner planets. A galaxy that reaches in from outside and periodically stirs the edges of the system with tidal forces we can calculate but cannot prevent. The solar system is not peaceful. It is not safe. It is not designed for us. It is ancient, violent, and enormous. And we are very small, very briefly present, and extraordinarily fortunate to exist within it at all. That is where we live. That is what we live inside. And knowing it fully, understanding it clearly, without the comfort of the diagram's false tidiness, is not cause for despair. It is cause for something more honest, and in the end more interesting. Genuine astonishment that in the middle of all of this, on one small rocky world protected by a thin magnetic field, and a shallow ocean of air, a species arose that could look up, figure out what was there, and understand it well enough to feel the appropriate size of what it had found. That is tonight. That is where you are. Inside the most violent neighborhood you will ever call home, looking up at it with eyes that can actually see what's there. There is one more thing that deserves to be said before we finish. Every meteorite that lands on Earth carries within it a piece of the solar system's history that no spacecraft has retrieved for us. The most primitive meteorites, the carbonaceous chondrites, are largely unchanged samples of the material from which the solar system originally formed 4.6 billion years ago. Some of them contain grains that predate the solar system itself, pre-solar grains formed in the atmospheres of stars that existed before the sun was born, tiny diamonds that crystallized around ancient carbon stars, silicon carbide particles from stars at the end of their lives. These grains survived the collapse of the molecular cloud that formed the solar system, survived the accretion of the rocky planets, survived billions of years as part of asteroids in the belt, survived atmospheric entry, and have been sitting in laboratories on Earth where scientists have analyzed them directly. You can hold a piece of a star that died before our sun existed. The meteorite record also preserves the fingerprints of the solar system's early violence in a physical and chemical way that no other source does. Some meteorites show evidence of rapid, intense heating and cooling consistent with being caught near the shock fronts of early impacts on their parent bodies. Others carry evidence of aqueous alteration, the chemical traces of contact with liquid water, meaning that even before the planets were fully formed, some small rocky bodies were warm enough from internal radioactive decay to carry liquid water in their interiors. The early solar system was, apparently, already wet in places long before Earth formed. The record of that early water survived the intervening billions of years locked in rocks that eventually fell out of the sky. Somewhere in an Antarctic ice field right now, today, meteorites are sitting on the blue ice where they have been concentrated by the movement of glaciers, waiting to be collected on the next season's research expedition. The ice preserves them. The blue color of the wind-scoured ice makes them visible against the white background. Teams of researchers travel to Antarctica specifically to collect them, because the ice field acts as a natural accumulation zone where meteorites from the entire Antarctic region collect over thousands of years. These samples, gathered from the surface and sent to laboratories around the world, represent an ongoing scientific return from the solar system's history that requires no rocket, no spacecraft, and no budget beyond a cold-weather research expedition. Small pieces of asteroids, comets, and the occasional fragment of Mars or the Moon are landing on Earth continuously. In the time it takes you to finish watching this video, extraterrestrial material has settled through the atmosphere and reached the ground somewhere on this planet. Most of it is invisible, microparticles that blend into the dust of the world. But it is there, arriving every minute, a constant gentle rain of solar system history falling onto our planet from the sky. We live inside a violent, ancient, extreme system, but we also live inside one that continuously sends us fragments of its own record. The solar system is violent, and it is also, in this particular sense, generous. It destroys and it delivers. It has bombarded this planet for billions of years, and it has, in the process of doing so, delivered water, organic molecules, and heavy elements that contributed to the chemistry of life. The violence and the generosity are the same thing, operating by the same physics, driven by the same orbital mechanics, and producing simultaneously both the greatest threat the solar system poses to complex life and one of the primary raw material supply chains for that life's origin. That is not a comfortable thought. It is an accurate one. And accuracy, ultimately, is what the solar system deserves. It has been here for 4.6 billion years, running its violent, extraordinary, complex machinery without reference to our comfort or our understanding. The least we can do, now that we are briefly here, and briefly capable of understanding it, is to see it clearly. Look up. Not at the diagram, at the thing itself. The star that has been exploding continuously for 5 billion years. The neighborhood of billions of rocky projectiles on orbits governed by gravity. The frozen outer shell where comets sleep until the galaxy stirs them awake. The hidden oceans under distant ice. The storms larger than worlds. The rings that won't be there in a geologic eye blink. The neighboring planets wearing their failed conditions like cautionary inscriptions. This is where you live. The most violent place you will ever call home, and it is genuinely astonishing. We have spent this entire video working through the layers of what the solar system actually is, and it is worth pausing before the end to note what that exercise requires of us. It requires a willingness to replace a comfortable, familiar picture with an accurate, less comfortable one. Most people encounter the solar system for the first time in a classroom or a children's book, at an age when the priority is accessibility, and the result is inevitably a simplification that leaves out the most interesting and most alarming parts. The planets are introduced as objects with names and colors and sizes. The order of their distances is taught as a sequence to memorize. The sun is described as the star at the center, the source of warmth and light. All of that is true. None of it is complete. The complete version requires understanding that the sun's warmth and the sun's violence are the same thing, the output of the same nuclear process, expressed in ways that are life-giving at the surface of a well-protected planet and lethal everywhere else. It requires understanding that the friendly, familiar moon hanging over the night sky is the remnant of a collision that nearly destroyed the early Earth. That Venus, our nearest neighbor in space, is a world where our best hardware survives for about 2 hours before being consumed by the environment. That the asteroid belt is not a static feature, but a gravitational machine continuously processing its contents and redirecting a fraction of them toward us. That the outer solar system contains objects whose orbits are unstable on million-year timescales, which means those objects are already on their way, in the only sense that matters across those timescales, toward the inner solar system. That the galaxy itself can reach in through the Oort cloud and perturb things, and that it does. The complete version also requires holding alongside all of that something else. The fact that we are here, understanding it. That is not a trivial fact. It required billions of years of the right conditions maintaining themselves on this particular planet. It required the late heavy bombardment to subside without sterilizing the planet's surface so thoroughly that life could not recover. It required plate tectonics to regulate the atmosphere across geological time. It required a magnetic field to hold back the solar wind for long enough that complex life could evolve. It required Jupiter to stay in its nearly circular outer orbit and not sweep through the inner solar system on a trajectory that would have relentlessly disrupted any delicate biological chemistry trying to establish itself on a rocky inner planet. It required a large moon at the right distance to stabilize the axial tilt and thereby stabilize the climate over the billions of years that the evolution of complex life demands. And it required the universe to be the kind of place that sometimes produces those conditions. A universe governed by physics that allows stars to fuse hydrogen into heavier elements for billions of years. A universe in which gravity produces planetary systems. A universe in which chemistry and liquid water can, under the right conditions, assemble itself into self-replicating molecules and eventually into organisms capable of looking up and asking what they are looking at. All of that happened. Against what would initially seem like remarkable odds, given the general level of violence and extremity in the solar system, all of that happened here, on this planet, during this window of the sun's long life, when conditions happen to permit it. The solar system will not always permit it. The sun will continue to brighten. In 1 billion years, complex surface life on Earth may no longer be possible. In 5 billion years, the sun will exhaust its hydrogen and begin its expansion toward a red giant, erasing the inner planets and whatever remains of this moment's solar system architecture. The rocks will survive. The Oort cloud will survive, dimly orbiting a cooling white dwarf. But the window during which any of this is understandable to any mind within it will be long closed. We are inside the window now. The window is, by the sun's timetable, already approaching its final phases. By our timetable, it still spans a genuinely enormous reach of time. Hundreds of millions of years, perhaps, before conditions at Earth's surface become truly incompatible with the kind of complexity that makes understanding possible. That is a genuinely long time, long enough to feel, from inside a human life, essentially infinite. Long enough that the urgency of any individual moment within it can feel trivial by comparison. But the solar system is not a place that operates on human timescales. It never has been. It runs on timescales of billions of years, and within those timescales, it has produced here, briefly, something that can look at it and understand it. That is the thing worth carrying away from tonight. Not anxiety, not despair, not the comfortable false reassurance of the diagram that says everything is fine and orderly and spaced out just right. Something more honest than any of those. Genuine wonder at the specific and improbable fact that inside one of the most violent environments imaginable, the physics nonetheless allowed, just once that we know of, for something to arise that could look at it and see it clearly. That is where we are. That is what we are. That is what tonight was about. And now you know. If you stayed with this all the way to the end, thank you. The real solar system is harder to sit with than the diagram. It asks more of you. It replaces comfort with accuracy and familiarity with something stranger and larger and truer. But the accurate picture is also the more interesting one, the more worth understanding, the one that actually corresponds to the place where you have spent your entire existence. Every clear night when you look up, you are looking into an ancient, violent, extraordinary machine. You have always been inside it. Tonight, maybe, you can see it a little more clearly for what it actually is.